Yes. Okay, so welcome. I'm Stefan Neumann, a corporate trainer with C.C.JENSEN, and I've also been working as a Noria's licensed partner for 7 years through the company Clean Oil Consult. The certifications here, Machinery Lubrication Technician and Machinery Lubrication Analyst, are some exams you can take through the ICML and typically working together with the Noria courses. I also run these courses in Denmark, Norway, and Sweden. I'll get back to that. So this is the third of the webinar in a series where we'll have talked about oil maintenance. Today we're going to talk about best practices in oil sampling, something about analysis and which kind of analysis will show that the oil is in good shape and the machine, and we'll talk online monitoring and a few cases. So I know it's going to be a good session, so if you have questions, please type them into the message field and then we'll come back to them. So as we did with the others, just starting briefly on the main problem with oil is, of course, that it's like the lifeblood in the machine. So if the blood is harmed with the particles or water, or could say it's ill, like the blood in your body, it will harm the machines, gearboxes, hydraulics, and so on. So during operation of any kind of machine, you will be contaminating the system and the oil with particles, water, acidity, and oxidation is part of the same thing. That will reduce the lifetime of the machine and the oil. It will also harm the reliability, and it will destroy the efficiency of the machine. And many studies have shown that 80% of oil-related system breakdowns are actually due to contaminated oil. So we can save a lot of money here by reducing the contamination in the oil. And today we'll look at how we can actually measure how much contamination we have. So the core of the business here for C.C.JENSEN is working with what we call kidney loop or offline filtration. So we are taking drawing the oil from the bottom of the sump, so the gearbox, the tank, the hydraulic system, the turbine, and running it slowly through the filter in a depth meter that takes a lot of dirt, a lot of water, and varnish out. It cannot be compared with the inline pressure filters because they live a very tough life where every start and stop or control valves are being moved and so on will give a pressure shock in the system and create actually a release of particles in the inline filter. So if we look at the cost for removing contamination, it's gonna be reduced significantly if you use offline filters, primarily because the filters here, the depth media filters, take a lot of dirt out, 2 to 4 kilos per insert typically. It can also be more if you work with the quenching or you work with cement or these very dirty application mines and so on. And C.C.JENSEN was actually the first company in the world to work with this offline filtration. Like I said, I also belong to a group of people with the Noria licenseships, and so in Clean Oil Consult is a company subsidiary of C.C.JENSEN, and we are doing courses in Denmark, Norway, and Sweden, primarily Denmark, but consultant work and so on. So you're welcome to visit our website. Yes, so today we'll talk about oil sampling strategies, some simple on-site tests, oil analysis basics, and if we have time, we'll talk about oil handling best practices or storage. If we don't have time, you can still see the PDF of the material and read it yourself. And of course, Q&A is important at the end. So why do we change oil, or why do our clients do? Well, most of them are doing it on fixed intervals. It could be old habits. On this pump, we change it every year, or this gear, or whatever. Or it could also be, of course, from the manufacturers. The OEMs say that in the manual you need to change every 500 hours on this engine, or whatever it is. Could also be the class company or the class company or insurance companies that says you have to do it at specific intervals. Or of course, a lot of people just change the oil because it was dirty or wet. But what you should be doing is you should monitor the oil and look at the conditions. And based on what the oil analysis say, you can change the oil, but very often you can just keep it clean and in a good shape, and then look for the additives, look for oil degradation, viscosity, and so on. And if that's depleted, you change the oil, or maybe do a sweetening only. But you don't need to just change because there was water or dirt in the oil. Of course, there's a few things that we cannot save by filtration. So if you have a very low viscosity, like 20% lower of that of new oil, so let's say you have a ghee oil with a 320 oil, now 20% of that is roughly 650, so sorry, 65. So if you're down at something like 250 or in viscosity, you definitely need to change your oil. You need to do something. You cannot just keep on filtering. The same if you have an engine with too much fuel content in the lube oil, something like 2% or more, you have to do something. You cannot just filter it out. If the TBN again on an engine is too low, so the base number, and roughly that's 50% of new oil, you cannot do anything else than topping up or change some parts of the oil. A filter cannot get the TBN number back. If your additives are washed out or depleted in some other way, you also need to sweeten the oil, so add some additives or change part of the oil, maybe 20%. And of course, if it's a wrong oil or the mixed with the incompatible fluids, you need to do something right now. So, but apart from that, a filter can do a lot of things to help you. So when we're doing oil sampling and analysis, why do we do it? Well, you want to show in a good analysis that that the oil can be used continuously, so still be used. So are the properties and the additives still okay? What about the degradation product? Is it oxidation speeding up so varnish issues could occur very soon? Or what about the level of contamination? Are seals and breathers and filters still in good shape? And last but not least, what's about the condition of the machine? Is wear under control or is it speeding up? So that's the primary things why you're having oil analysis in the first place. When you're doing sampling, it's very important that you want to do a representative sample. That means that you have to do your utmost to take a sample that shows what is in the oil in the system, not just what was in the flushed or the valve you're using. So you need to flush the sample valve you're having or the sample cock, and use mini mesh, for example. Always use super clean or ultra clean bottles with a sealing on the cap, and fill in the label and send it right away to the lab. If you wait too long, for example, if you're working on turbine oils and you leave that in your car or in your office, the degradation rate, so the oxidation, will speed up quite significantly over time. So you want to send it right away, otherwise you'll actually get a wrong result on the varnish. Why not use an empty water bottle, or an old bucket, or let the oil run down a screwdriver into the sample bottle? Again, you want to show a representative sample, and in this case it's not, because you got the dirt from the old bucket, you got water in the water bottle, even though you think, oh, I cleaned it with some oil and so on. No, it doesn't work. I'll just give you some examples. So if you have a very clean oil, up to a more, could I say, semi-dirty oil on these here. So the more clean the oil is, the more careful you have to be. Think about it, if you're having a pool with water and it's very clean, nice water to swim in, if you add some mud, it's gonna look muddy. But if the pool was dirty and muddy in the first place and you add a little bit of mud, maybe it's still muddy. So you have to be much more careful if we are working with clean system than comparing to if you're working with more dirty system. So here, adding 1 drop of contaminated oil to an ISO 181512, it's actually, it doesn't show because you have millions of particles already. While if you have a very clean hydraulic or ghee oil at a 1073 and you add just 1 drop, you're certainly jumping up 5 ISO classes. Same goes with water. If you have a very dry system, now 0 ppm is not very often, but if you have a very dry system and just 1 drop of water, and you suddenly add 625 ppm. So very little contamination from your breath, for example water, or from the dust in the surrounding can actually harm the sample. That is also why we see online sampling are starting more and more to be popular, because you don't get influences from, you taking the sample, the lab doing wrong things and so on. So when we do take the sample, like I said, make sure that's representative. That means that the system has to be in a stable operation condition. That can be very difficult on some systems, especially if you have a wind turbine gearbox. You're not allowed to climb the wind turbine while it's in operation. So, and that means quite a lot on, if a gear is in operation, all the bearings, all the gears are like matched, well, but if you are idling or you're stopping, they're all loose and actually will release more particles. That's unfortunate. We can't do much about it on a wind turbine, but all the other systems where you can, please let them run. I mean, an engine has to be warm while you take the sample, or a hydraulic system, a gear system. Let it be warm, so in full operation. And the sample can be taken from a pressurized area near an elbow. That's because you want turbulent flow. It's best to take it if it's a pipe that lies down horizontal. It's best to take up here, not at outside or downwards, because the heavier particles will fall down. Or if you have near a bend, then they'll be shot out at the corner here. So if it's a vertical pipe, so going down, of course you can take it just out from the side. If you have an offline filter like a CTC filter and it's operating continuously, you can also sample from this sample point, because, well, it's taking from the bottom, but if it's running continuously, obviously you will have this sum be mixed. So after a couple of rotations here, you have exactly here as you have here. So it's okay. If the system was not in continuous operation, you shouldn't be using it. I mean, if you have a mobile CTC filter and you couple it up and take a sample, that will not be correct, because that will be exactly from the bottom. Maybe it's good if you want to sell a filter, but it's not good for a representative sample. So how do you do it? Well, if you have like showing here on a CTC filter, but some other, where it's just a sample valve that you open, you need to close the valve a couple of times, something like 5 times, to make sure you break loose some particles that were in the valve. Then you need to flush the pipe, and that's the theory is 10 times the volume that was in the pipe has to flush through. We cannot calculate that, so typically we say half a liter to a liter of oil into a bucket. Then you open your sample valve, your sample bottle, and you put it into the oil stream without touching anything. Fill it roughly 80%, and then close the lid. And then you close the valve, not before. So do it as fast as possible, because the longer time you got the cap off the sample bottle, the longer or the bigger the risk for particles to entering, and water and other things. Even if you're in very dusty environment, you could actually take a plastic bag or put the sample bottle in a plastic bag and puncture the plastic bag just when you are doing the sample, so you don't get dust in. Here's just written in text, and of course you also need to fill in some information about the system. So sample date, who sampled it, the sample point, running hours, all these kind of things. And why is that the case? Well, it's like if I went to the doctor to have a blood sample. I want to make sure that I get the results back from my blood sample and not the neighbor's. So I want to make sure I have as much information as possible to be able to compare this sample with the previous sample and the previous again. Sampling is all about trending, so you need to typically look back 3, 4, 5 samples and see the trend. If you're using Minimesh, that's also a very good way to sample. You can see here the dead lake is very, very short, so you only need to flush very briefly, and the hose here, as soon as you connect it to the Minimesh, the flow will start. Remember to clean the with a detergent, or use a new hose every time. If you're using vacuum pumps and these coiled up hoses. Again, please be aware that the coiled up hose is really difficult to straighten and get in the right position you want. So you want to actually with tie wraps or something strap it onto a rod or something so you know exactly where you put it in the gearbox. Otherwise it's very difficult to know where it's going, and maybe it's actually getting in between the teeth and being the plastic will be eaten up by the gear teeth, or you'll be scraping down the varnish from the sides and so on. So please be careful with vacuum pumps. The best way to use a vacuum pump is actually if you had installed one of these mini mesh with a long, I think it's called a pitot tube. So here it's down here, so it could look like you're actually sampling from the corner, the bottom here of the gearbox, but you're not, because this long pipe is pointing upwards, so you're drawing a sample near the gears. So yeah, you need to of course flush it first because the pipe is dirty inside, but when you have done that, you can do a very good representative sample from this gearbox. And there's no other ways to do it actually, because there's no pressurized line coming out. So that makes sense to install something like this. Also, what makes good sense is to have a number of sample points. So you have your primary sample point, and in this case this is the one here just before the filter, so on the return line from all the valves, all the cylinders, all the hydraulic motors. Could also be on turbines and so on, where you have a number of bearings. You want to have a primary sample point just before the tank, before the filtration, before the tank, and then maybe a sample point under each bearing or each cylinder, hydraulic motor. So if you see there's issues, you can go up and take a secondary sample and see which of these components are actually faulty. Now in this case here, the primary target for this system was an ISO code 181512. Now this one is from Noria, so they in the US very often you don't have 3 digits in the ISO code, you only have 2. So 1815, is that the same as this? No, it's not. This is 2018-15. When you're missing the first of the 3, it's always the one with the tiniest particles you're missing. So that will be equal to a 2018-15. So this is above what you want. Your target is 18-15-12, so this is higher. So you want to have a look at where are the actual particles being generated, and it looks like in this case it's actually the main pump. You can see the case drain here, so the main pump is generating a lot of wear. Yes. So if we look at some very quick on-site test you can do when you're out, or the client can do, and you don't need to send it to a lab, there's a few things you can do. First, actually visually, the best sight glasses are really big sight glasses, so you can get maybe a flashlight on them, or like this one you actually have both a sample point, a mini mesh, you have a magnet going through, so it could see, well, if this is looking like a hedgehog, I know there's some big problems in this gearbox or whatever it is of system, so I can see the color, I can see foam, I can see varnish and so on. So visual is also good. Also, if you draw the sample, look at the bottle itself. Can I see through it, can I not, and what kind of things. Also, you can do the quick and what is called a crackle test. So you put a drop of oil onto a hot plate and look at if it's bubbling or crackling, and the crackling sound. Well, it says here below 500 ppm. You don't have any audible or visual bubbles. I would say you have to be very skilled to do that. Most people are saying around 1000 ppm. So 0.1%, when it's in that region, that's when you start to see some crackling and bubbles and so on. That's what they're using in most labs. If it's just a screening test, so not a Carl Fischer water titration test, but just looking at the quickly if there's some water. Also, if you have an turbine oil or a thruster or something where you want to make sure you can shed the water out of the oil, you can mix the oil in half water, half oil, and then see if it separates out. And the rule of thumb, as you may recall, is 20 minutes. If they separate quicker than 20 minutes and you have no emulsions in the middle, then it's good. And of course, if you see it's quite slow and you do see some emulsions, I would make a lab do it, because the really test, the lab test, is at 54 degrees C, very weird, and 40 milliliters of oil, 40 milliliter of water, and they mix it for 5 minutes and then, you know, let it separate out. We can't do it so accurately ourselves, so I will have a lab do it. But you know, it's important if you're using a filter separator, for example, or if you are making sure that the separability of a turbine oil is still okay. And last, you can do a pad test. So this is a kit you can get just with a funnel and a vacuum pump. So you pour in to the funnel here, you pour the oil and the same amount of solvent, and then you draw it through a membrane. Typically the membranes are 1.2 micron, but you can get the 0.45 microns that are called MPC, so for varnish. And then you let the pads dry and you can see the stain, or put it into a microscope and see the soot, the varnish, the particles, and so on. It is a little bit, the solvent is not healthy, so please be aware that you have, if you do that yourself, don't do it in your kitchen or something. It's really smelly, so you need to have a good, you know, breathing system or a good, you know, ventilation system. I know it's been done on many ships, and I think in the old days there were not that much concern about your brain cells, but I would not recommend it just to do it, you know, in your garage or in your kitchen or something. There's a few others, of course. You can cool the oil down in your fridge at night, and if it starts to be very, could I say, like cotton candy inside, there's actually varnish in it. There's also blotter spot test for engines, where you drop a drop of oil onto a kind of a paper, and so there's many different tests. If we go have a look at the oil test that you can do online, so meaning a sensor that you put in. Most known are the optical light blockage sensors. So this is like the CTC sensor here, the OCM, or all others more or less in the world that you can buy. They typically look at ISO counts, so 4 micron, 6 micron, 14 micron and up, and mostly stop around 250 microns. If you want to look at bigger particles, you have to go with the inductive sensors, the wear debris sensors. There's also one from C.C.JENSEN. Most of them start around 100 micron. The ones C.C.JENSEN have start at 40. But the good thing is there you also see the big ones. If you look at let's say a 250 micron particle, so very big wear debris from a gearbox, that 1 or 2 or 5 particles will be completely invisible in a small optical sensor, because there are just 5 of them compared to millions of all the other particles. So that's why your wear debris sensors are more accurate, because they can actually see just very few particles. You can also have oil quality sensors. C.C.JENSEN have this, what they call the OQM sensor. There are other people that have, I know there's one called 10 Delta, and these kind of sensors are not measuring, you know, varnish very accurately, but they are giving you a trend, like you can see here, what happens over time. Now this was a very hot hydraulic oil over 2.5 months that was stressed in this system, so you can see the trend goes upwards. So it shows you that oxidation or varnishing is happening, but it's not a sensor, neither the CTC sensor or the others in the market is not a sensor that you can come with a mobile kit, plug it in and say, whoops, the varnish is at this level. It's not designed for that. It's designed for a trend. So you have to compare, you know, many samples, so many weeks, and then you can see where the trend is going. If you want an accurate just here and now, there's unfortunately no online sensors. There's only the MPC or other measures that you can do in a lab. So if you're having online monitoring, so sensors for oil quality, for wear debris, for particles, maybe even viscosities and water and all these kind of things, you send these data into system, could say mining system, a software, and that is typically, taking the data and using simulation models or knowledge of oil systems, statistical models, and so on, and using that to give some treated data, so what is going on onto a system expert, or it could also be the raw data. He may combine these information with vibration analysis and so on, but what you want to have then is some interface on the web that you can see what's going on with this machine, or you want to do some report saying this and this is happening, and we recommend that you take these actions or precautions, and maybe even warning on text or email that now you have surpassed the recommended level for water or for cleanliness in particles and so on. And when we do online particle samples compared to a bottle sample, there's a few things we need to be aware of. First is that if you're doing a bad job for the sample, or the customer is, and the lab is doing a bad job, then you'll get something that is not trendable, because it is getting dirt and water and so on from all other sources. So if we look at here, you have the cleanliness of the y-axis and the system, how dirty or how clean it is on the x-axis here. So a very dirty system may have an ISO count of 25, 23, 20. This if the same system was extremely clean, but you do a bad job at sampling, or the client, the lab is doing a bad job, the particle counters are maybe not up to date and so on, then even a very clean system will show a very high ISO code. So maybe an 18, 16, 13. So this is not trendable. It's because you're getting dirt from anywhere else. If you do the utmost yourself, you have an ultra clean bottle, and you have a good manual particle count, or a very good microscope, or whatever you're using, then there's a big difference when the system is clean, because now you could have maybe a reduction of 5, 6 ISO classes in between here, and this is just what the lab, what the guys sampling and so on have added to the sample. So this is trendable. So here, when the system is getting more and more dirty, you'll see the ISO counts will go up significantly. Of course, when the system is very dirty, they are very close to each other, these two curves, because when you're having, let's just say, 20 million particles in 100 milliliters, you have to add a lot from the surrounding to destroy those 20 million. They will vary, they will be 20 million and 2,000 particles, and that's of course not a difference. When you then have online sensors, be aware that even the best, the sample bottles you can buy, have an ISO code of 8 in 4 micron. So there will be a difference from a online sample point where there's whether it's the sensor is measuring without any bottle, without interference from you guys, from the lab, from anything else, there will always be a difference. So maybe the difference is 2, 3, 5 isocoses maybe in difference between a very clean system and the more dirty here. The dirtier it is, the closer they're getting together. Again, like I said, you are having millions of particles, so then the few particles from the bottle and the lab means less. But when it's very, very clean, the sample bottle, the person involved and so on means quite a lot. And then there are a lot of sensors out there that have decided, that the company making them, that will not go cleaner than something, let's say 8. So an ISO code 10 or 8, that's where they stop. So ISO code 1086, for example, that is the lowest they can measure, and that's because they know that you can never do that with a sample bottle, so that's where they're stopping. But in fact, you can go cleaner if you have the best systems that are insensitive to air and water, like the CJC OCM. Then you could get very close to 0. And is that incorrect? It's actually not. It depends, of course, on the system. But I've seen some, like a hydraulic system, pitch system on a wind turbine. It only had 250 liters of oil, and the filter was 2727 that was circulating 250 liter an hour. So you are circulating the full volume of the oil in the system every hour. And when the pitch is not in operation, when the turbine is standing still, of course you're getting very, very clean oil. So yes, you're getting close to zero particles. Of course you are. You're having an efficiency of 98% in the filter, and you're circulating it many, 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 many times, the same oil. So therefore it is getting close to zero. So that's why we had, we accept that it can get very close, like a 530 or something, or even close to 000, if the system is, not generating particles. A lot of other particle counters out there, they had just decided to stop at something like an 10 or an 8. So when you're using online particle counters, what could then help you in real life? Well, here's a case here from a wind turbine in Germany. It was installed in 2005, and they had issues after about 10 years. You could see that the ISO code is really high, and they did an endoscope showing that there was a failing of the planetary gearbox and 7 of the bearings. The challenge was that this was in a inaccessible location, so they had to make a concrete slab for the crane. They had to clear cut some trees in order to get there and repair the gearbox. So they scheduled the repair for 2016. So now you have more than 1 year where you need to operate the turbine. Is that possible? Yes, if you downgrade, because the more power you have on the turbine, the more torque, the more pressure you have on the gears. So they downgraded the output from 2 megawatt to 1.5 megawatt. Then they put on a CDC filter with 3 micron depth filter and an online particle counter to follow the trend. So we started at a 211917 ISO code, so very dirty, and after the following months we're down to a 15129, so really clean oil. But then something happened on July 8th. The alarm was triggered by the ISO count. What happened? You can see here the the general ISO codes are really, really good here. So 14, 15 in that region for the 4 micron, and then suddenly it's spiking up. So what happens? Well, if we zoom in, you can see on July 4th the turbine was stopped. And by accident, it was actually reset. The software was reset to 2 megawatt again. So when they start up the turbine, you have a spike. That's quite normal to have a spike when you're starting up a gearbox again. But the particles, only go slow down. And that's because we cannot keep up. We're generating too many particles compared to what the filter can remove. Now we're running full load. The same thing again, so just zooming in so you can see here it's really low, so something like a 20/18/15 on full load, which is of course not good for a gearbox, especially not one that is worn. So on July 8th we contacted the client, said that and they told us that the software was reset by mistake, so they reduced it to 1.5 megawatt, and now you can see you're starting to cleaning up the ISO codes, and actually it ran trouble-free for 9 months until the scheduled repair. That is a huge amount of money. So you don't get a complete failure of the gearbox and bearings and so on, and you can generate power in a turbine 9 months. Yes, it's only 1.5 megawatt instead of 2 megawatt, but it's definitely much more than 0 megawatt in 9 months. So here an online sensor and a filter saved a gearbox and saved the client here for a lot of money. Yes, so there's very good things you can do with online particle counting, and I think it's going to be the future, and also other kind of sensors. Still, of course, we have our normal oil analysis that you draw a sample, send it to a lab, and there's a typical, you look at viscosity, acidity, that would be 10 for, or AN number for hydraulic turbines and so on, and for TBN is for engine oil, so base number instead. You're gonna look at contamination, so particles and ISO counts. If it's weight percentage, that will be for engines, or quenching or something where it's very dirty, and a quick crackle test for the water. then you'll look at wear, ppm of iron, copper, and so on by this ICP, so element analysis. That's typically what is done. If there's something critically happening or it's a very important application, you would measure water by coefficient instead. This is much more accurate. You could measure like 123 ppm or whatever it is, and not just roughly 1000 and above. You could also use the ferrous density test, PQ or VPC, very important for gearboxes and heavy loaded machinery, because they will look at ferrous metal, so magnetic metal, how that is showing up in the sample. And you're gonna look at more details on the additive level, so zinc, phosphorus, calcium, and whatever you have. Or you may look at amines and phenols by the ruler if you have turbine oil, for example. Oxidation and varnish is also very important tests for critical systems, so hydraulic system and such, and turbines. MPC is the most used, membrane patch colorimetrics. Ultracentrifuge is also used by a lot of people, and FTIR is used because it's quite cheap, but it's not very accurate showing varnish levels. And obviously there's a lot of other tests depending on the machine type, so you will have flashpoint for engines, demulsibility for steam turbines, RPVOT, oxidation test for turbines, foam test for gear oils, and so on. So if you look at the different sample, what will show that there's actually a, could you say, a condemning limit where you need to do something right now. Very seldom it's actually particle of water, because you can just clean it and filter the oil. If you're looking at gear oil, for example, a thruster or another gear type, it's normally viscosity that is the most important thing to look at. So new oil plus or minus 15%. If you're not within this limit, you need to do something right now. If the additives are depleted, so the new level minus 50%. If your acidity is too high, again, it's new oil comparing to, so plus 1. So if the new oil has a 0.5 in TAN, then a 1.5 would be your critical level. If the oil is degraded, so you're having varnish in, normally it's around 30. I would say if it's a very critical system, maybe even lower. And if you cannot separate water anymore, for example, demulsibility is higher than 30 minutes. There you have some condemning limits for this gear oil. If you're looking at hydraulics, it's very, very close to being the same as the gear oil. You can see viscosity is the same, acidity is the same, degradation is the same. Maybe if it's a very critical system, again, I would maybe go to MPC 20 or below. And then you have an extra one here, soot for microdieseling. So if the oil is turning very black, the oils you can see here, that's an oil that has degraded into this brown. That's a normal degradation. But if the oil suddenly turns black, like grayish black color, it's actually air that is being compressed in a high pressure pump and then cracking the oil or destroying the oil. That you can see quite often in hydraulic systems using these ester-based fluid. So EHC systems, control system for turbines, have that issue quite often. You may also in some hydraulics test for foam, or you may test for air release and so on. But these are the basic tests. Engines, you're gonna look at again viscosity here. Minus viscosity is not as cannot be allowed as much as the plus. So if your viscosity is increasing, that could be due to a lot of soot, a lot of varnish. The engine can still run okay, but low viscosity, it can be very critical. That would be fuel content typically. If the base number is below 50%, it's critical. If you have fuel dilution, if you have a flash point that is too low, if you have too much insolubles, that's soot, more than 1.5%, and if the additives are depleted. Now, insolubles is the right way to measure a dirty oil, so not ISO count. I know some labs say they could do ISO counts on engine oils, but it's very inaccurate, because what they do is they dilute the oil with the solvent, and maybe they're diluting it like 1 to 50. So they have 1 milliliter of engine oil into 50 milliliter of solvent and then measure the particle count. Come on, you're measuring the particle count on something else, the solvent, not the oil. So ask for insoluble instead. And the last one, the diesel, is actually very, very seldom that you need to, throw out diesel because of problems. So, but of course, if there's a lot of microbes and so on in, you can use a filter separator to remove the microbes and the water, of course, and filtration. I have not seen diesel that you have to, discard off just because it's dirty or microbes. Yes. So here coming to the end, this is a self-study, but so just briefly, when you're looking at an oil analysis, first you need, of course, to understand what kind of system you work with. Then you look at the properties, so viscosity, acidity, additives, oxidation. Then you look at the contamination, and finally look at the wear debris. So iron, copper, and so on that's coming off. Now for these 15 minutes today, of course, we can not go in depth, but there's a lot of good information out there. I'll just end here with a few examples what you can actually do with oil analysis. Now this is from a hydraulic system. Here it's put in, it's done in a very good way, I must say. It's put into these, this is a baseline, so this is my new oil, and then I have a caution column and a critical column. Then no matter, if the guy is knowing a lot about oil analysis or not, he can always compare the oil samples out here to the column. So am I in the critical or in the caution area? So the samples here you see January, May, October, December. Something happens. Yeah, I got way too many particles for hydraulic system. What else is happening? Well, if we skim it, you will see something happens with water as well. So there's getting a lot of water in. And to be honest, they should have looked here in January, because you're actually passing the critical limit here in January. But they didn't do anything. So water was coming in from a broken cooler, or maybe somebody's just, hosing down the system every evening, and you're actually spraying in water. That will start to generate some iron content. So you can see your iron is increasing. So 160 ppm of iron is a lot for a hydraulic system. What is funny is if we look at the ferrous density, so the metals that are magnetics, there's actually not a big going on, and that's because all the iron you see here is rust, and rust is not magnetic. So therefore, in this specific case, you cannot see much on the ferrous density test. The acidity is being reduced, and that's because you're actually washing out additives on the way when you're getting so much water in, and the varnish level you can see increasing and so on. So this is what you can use a sample in a hydraulic system. If we take the last one here on gear oils, again you got the base oil or the baseline so that is the new oil. You can see you got a lot of ZDDP in this oil, and you got some calcium. If they measured sulfur, you would also see that, because the EP additive is actually sulfur phosphorus, but they didn't do that. So in this case, you have a particle count increasing to very high levels for gearbox. The iron content is also increasing, going beyond. In April here, you're actually beyond your critical, so they should have acted. What is nice about this case, if you look at the ferrous density, you can see this is crazy high. High is typically when it's higher than the ppm level of iron. So if you're having, in this case, 26 iron here in April, 55 is more than double. So that means you're having a lot of abrasive and adhesive wear, so really big particles being generated by wear. And so in this case, you can see this is really, really critical. I like this because if they only looked at the elements, there's many labs that do not flag a gearbox before you are at 80 or 100 parts per million iron. So they would not have actually seen this. Now, yeah, you can see they would have, but some labs actually just put in 80 or 100, and then you wouldn't have flagged this. But you can see on the ferrous density test, the PQ test, that they are getting a lot of big chunks of wear. If they had an online particle counter that would look at the yeah, both isocodes, but maybe even the wear debris, you would see there's crazy amount of wear debris. This was actually because the gearbox and the motor was lined up wrong. So you're pushing you know, very hard on some edges of the gearbox, and that, yeah, of course you wear your teeth because they're not getting an even load. Good. So that was actually what we had. Like I said, if we had time, and we didn't, sorry about that, we have some oil handling best practices, and I'll just show you. There's a few slides here you can see, and you can read them yourself. There's just best practice on some, yeah, good ideas. So I'll be stopping this session. Just a second.